United States Patent 3,951,134 Mallet April 20, 1976 Apparatus and method for remotely monitoring and altering brain waves. Abstract apparatus for and method of sensing brain waves at a position remote from a subject whereby electromagnetic signals of different frequencies are simultaneously transmitted to the brain of the subject in which the signals interfere with one another to yield the waveform which is modulated by the subject's brain waves. The interference waveform, which is representative of the brain wave activity, is retransmitted by the brain to a receiver where it is demodulated and amplified. The demodulated waveform is then displayed for visual viewing and routed to a computer for further processing and analysis. The demodulated waveform also can be used to produce a compensating signal which is transmitted back to the brain to effect the desired change in the electrical activity therein. Inventors: Mallet, Robert G. Plainview, New York. Cassini, Dorn and Marco Lynn Incorporated. Bohemia, New York. Family ID 23,964,813 of numbered 05/494,518 filed August 5, 1970 for current U.S. class 600/544, 600/407 current CPC class Big 61B5/0006 20,130,101 A 61B5/0507 20,130,101 A 61B5/0476 20,130,101 current international class Big 61B5/00 20,060,101 A 61B5/0476 20,060,101 A 61B005/0 for field of search 128/1C1 R2.1 R419 R422 R420 404 to R2S2.5 R2.5 B2.5 F 2.6 or 340/248 A 258 A 258 B 258 D 229 References cited referenced by U.S. Patent documents 2,860,627 November 1958 Hardman Oak 3,096,768 July 1963 Griffith, Jr. 3,233,450 February 1966 Fry 3,483,860 December 1969 Nano 3,495,596 February 1970 Condite 3,555,529 January 1971 Brown et al. 3,773,049 November 1973 Rabiquette et al. 3,796,208 March 1970 for Glob's primary examiner. Com. William P. Attorney, agent or firm, Darby and Darby claims. What is claimed is 1. Brain wave monitoring apparatus comprising means for producing the base frequency signal, means for producing the first signal having a frequency related to that of the base frequency and at a predetermined phase related thereto, means for transmitting both said base frequency and said first signals to the brain of the subject being monitored, means for receiving a second signal transmitted by the brain of the subject being monitored in response to both said base frequency and said first signals, Mixing means for producing from said base frequency signal and said received second signal a response signal having a frequency related to that of the base frequency, and means for interpreting said response signal. 2. Apparatus as in claim 1 where said receiving means comprising means for isolating the transmitted signals from the received second signals. 3. Apparatus as in claim to further comprising a bandpass filter with an input connected to said isolating means and an output connected to said mixing means. 4. Apparatus as in claim 1 further comprising means for amplifying said response signal. 5. Apparatus as in claim for further comprising means for demodulating said amplified response signal. 6. Apparatus as in claim 5 further comprising interpreting means connected to the output of said demodulator means. 7. Apparatus according to claim 1 further comprising means for producing an electromagnetic wave control signal dependent on said response signal, and means for transmitting said control signal to the brain of said subject. 8. Apparatus as in claim 7 when said transmitting means comprising means for directing the electromagnetic wave control signal to a predetermined part of the brain. 9. A process for monitoring brain wave activity of a subject comprising the steps of transmitting at least 2 electromagnetic energy signals of different frequencies to the brain of the subject being monitored, receiving an electromagnetic energy signal resulting from the mixing of said two signals in the brain modulated by the brain wave activity and retransmitted by the brain in response to said transmitted energy signals, and interpreting said received signal. 10. A process as in claim 9 further comprising the step of transmitting the further electromagnetic wave signal to the brain to vary the brain wave activity. 11. A process as in claim 10 when the step of transmitting the further signals comprising obtaining the standard signal, comparing said received electromagnetic energy signals with said standard signal, producing a compensating signal corresponding to the comparison between said received electromagnetic energy signals and the standard signal, and transmitting the compensating signals to the brain of the subject being monitored. Description: background of the invention. Medical science has found brain waves to be a useful barometer of organic functions. Measurements of electrical activity in the brain have been instrumental in detecting physical and psychic disorder, measuring stress, determining sleep patterns, and monitoring body metabolism. The present art for measurement of brain waves employs electroencephalographs, including probes with sensors which are attached to the skull of the subject under study at points proximate to the regions of the brain being monitored. Electrical contact between the sensors and apparatus employed to process the detected brain waves is maintained by a plurality of wires extending from the sensors to the apparatus. The necessity for physically attaching the measurement apparatus to the subject imposes several limitations on the measurement process. The subject may experience discomfort, particularly if the measurements are to be made over extended periods of time. His bodily movements are restricted and he is generally confined to the immediate vicinity of the measuring apparatus. Furthermore, measurements cannot be made while the subject is conscious without his awareness. The comprehensiveness of the measurements is also limited since the finite number of probes employed to monitor local regions of brain wave activity do not permit observation of the total brain wave profile in a single test. Summary of the invention. The present invention relates to apparatus and a method for monitoring brain waves wherein all components of the apparatus employed are remote from the test subject. More specifically, high-frequency transmitters operated to radiate electromagnetic energy of different frequencies through antennas which are capable of scanning the entire brain of the test subject or any desired region thereof. The signals of different frequencies penetrate the skull of the subject and impinge upon the brain where they mix to yield an interference wave modulated by radiations from the brain's natural electrical activity. The modulated interference wave is retransmitted by the brain and received by an antenna at a remote station where it is demodulated and processed to provide a profile of the subject's brain waves. In addition to passively monitoring his brain waves, the subject's neurological processes may be affected by transmitting to his brain, through a transmitter, compensating signals. The latter signals can be derived from the received and processed brain waves. Objects of the invention. It is therefore an object of the invention to remotely monitor electrical activity in the entire brain or selected local regions thereof with a single measurement. Another object is the monitoring of a subject's brain wave activity through transmission and reception of electromagnetic waves. Still another object is to monitor brain wave activity from a position remote from the subject. The further object is to provide a method and apparatus for affecting brain wave activity by transmitting electromagnetic signals thereto. Description of the drawings. Other and further objects of the invention will appear from the following description and the accompanying drawings, which form part of the instant specification and which are to be read in conjunction therewith, and in which like reference numerals are used to indicate like parts in the various views. Figure 1 is a block diagram showing the interconnection of the components of the apparatus of the invention. Figure 2 is a block diagram showing signal flow in one embodiment of the apparatus. Description of the preferred embodiment. Referring to the drawings, specifically Figure 1, a high-frequency transmitter produces and supplies to electromagnetic wave signals through suitable coupling means 14 to an antenna 4. The signals are directed by the antenna 4 to the skull 6 of the subject being examined. The two signals from the antenna 4, which travel independently, penetrate the skull 6 and impinge upon the tissue of the brain 10. Within the tissue of the brain 10, the signals combine, much in the manner of a conventional mixing process technique, with each section of the brain having a different modulating action. The resulting waveform of the two signals has its greatest amplitude when the two signals are in phase and thus reinforcing one another. When the signals are exactly 180 degrees out of phase, the combination produces a resultant waveform of minimum amplitude. If the amplitudes of the two signals transmitted to the subject are maintained at identical levels, the resultant interference waveform, absent influences of external radiation, may be expected to assume zero intensity when maximum interference occurs, the number of such points being equal to the difference in frequencies of the incident signals. However, interference by radiation from electrical activity within the brain causes the waveform resulting from interference of the two transmitted signals to vary from the expected result, i.e., the interference waveform is modulated by the brain waves. It is believed that this is due to the fact that brain waves produce electric charges, each of which has a component of electromagnetic radiation associated with it. The electromagnetic radiation produced by the brain waves in turn reacts with the signals transmitted to the brain from the external source. The modulated interference waveform is retransmitted from the brain 10 back through the skull 6. The quantity of energy is retransmitted sufficient to enable it to be picked up by the antenna 4. This can be controlled, within limits, by adjusting the absolute and relative intensities of the signals originally transmitted to the brain. Of course, the level of the transmitted energy should be kept below that which may be harmful to the subject. The antenna passes the received signal to a receiver 12 through the antenna electronics 14. Within the receiver, the wave is amplified by conventional RF amplifiers 16 and demodulated by conventional detector and modulator electronics 18. The demodulated wave, representing the intrabrain electrical activity, is amplified by amplifiers 20 and the resulting information in electronic form is stored in buffer circuitry 22. From the buffers 22 the information is fed to a suitable visual display 24, for example one employing a cathode ray tube, light emitting diode, liquid crystal, or a mechanical plotter. The information may also be channeled to a computer 26 for further processing and analysis with the output of the computer displayed by heretofore mentioned suitable means. In addition to channeling its information to display devices 24, the computer 26 can also produce signals to control an auxiliary transmitter 28. Transmitter 28 is used to produce a compensating signal which, if transmitted to the brain 10 of the subject 8 by the antenna 4, in a preferred embodiment of the invention, the compensating signal is derived as a function of the received brain wave signals, although it can be produced separately. The compensating signals affect electrical activity within the brain 10. Various configurations of suitable apparatus and electronic circuitry may be utilized to form the system generally shown in Figure 1, and one of the many possible configurations is illustrated in Figure 2. In the example shown therein, two signals, one of 100 mHz and the other of 210 mHz are transmitted simultaneously and combined in the brain 10 to form a resultant wave of frequency equal to the difference in frequencies of the incident signals, i.e., 110 MHz. The sum of the two incident frequencies is also available, but is discarded in subsequent filtering. The 100 mHz signal is obtained at the output 37 of an RF power divider 34, into which a 100 mHz signal generated by an oscillator 30 is injected. The oscillator 30 is of a conventional type employing either crystal for fixed frequency circuits or a tunable circuit set to oscillate at 100 MHz. It can be a pulse generator, square wave generator, or sinusoidal wave generator. The RF power divider can be any conventional VHF, UHF, or SHF frequency range device constructed to provide, at each of three outputs, the signal identical in frequency to that applied to its input. The 210 mHz signal is derived from the same 100 mHz oscillator 30 and RF power divider 34 as the 100 mHz signal, operating in concert with a frequency doubler 36 and 10 mHz oscillator 32. The frequency doubler can be any conventional device, which provides at its output a signal with frequency equal to twice the frequency of a signal applied at its input. The 10 mHz oscillator can also be of conventional type similar to the 100 mHz oscillator heretofore described. The 100 mHz signal from the output 39 of the RF power divider 34 is fed through the frequency doubler 36, and the resulting 200 mHz signal is applied to a mixer 40. The mixer 40 can be any conventional VHF, UHF or SHF frequency range device capable of accepting to input signals of differing frequencies and providing to output signals with frequencies equal to the sum and difference in frequencies respectively of the input signals. The tandem HD signal from the oscillator 32 is also applied to the mixer 40. The 200 HD signal from the W36 and the tandem HD signal from the oscillator 30 to combine in the mixer 40 to form a signal with a frequency of 200 tandem HD equal to the sum of the frequencies of the 200 MHz and tandem HD signals. The 200 tandem HD signal is one of the signals transmitted to the brain stem of the subject being monitored. In the arrangement shown in Figure 2, an antenna 41 is used to transmit the 200 tandem HD signal and another antenna 43 is used to transmit the 100 HD signal. Of course, a single antenna capable of operating at 100 MHz and 200 tandem HD frequencies may be used to transmit both signals. The scan angle, direction and rate may be controlled mechanically, e.g., by a reversing motor, or electronically, e.g., by energizing elements in the antenna in proper synchronization. Thus, the antennas can be of either fixed or rotary conventional types. A second 100 MHz signal derived from output terminal 37 of the three-way power divider 34 is applied to a circulator 38 and emerges therefrom with a desired phase shift. The circulator 38 can be of any conventional type wherein the signal applied to an input port emerges from an output port with an appropriate phase shift. The 100 MHz signal is then transmitted to the brain stem of the subject being monitored via the antenna 43 as the second component of the dual signal transmission. The antenna 43 can be of conventional type similar to antenna 41 heretofore described. As previously noted, these two antennas may be combined in a single unit. The transmitted 100 and 200 tandem HD signal components mix within the tissue in the brain stem and interfere with one another, yielding the signal of a frequency of 100 tandem Hz. The difference in frequencies of the coincident components, modulated by electromagnetic emissions from the brain, i.e., the brain wave activity being monitored. This modulated 100 tandem HD signal is radiated into space. The 100 tandem HD signal, modulated by brain wave activity, is picked up by an antenna 45 and channeled back through the circulator 38 where it undergoes an appropriate phase shift. The circulator 38 isolates the transmitted signals from the received signal. Any suitable diplexer or duplexer can be used. The antenna 45 can be of conventional type similar to antennas 41 and 43. It can be combined with them in a single unit or it can be separated. The received modulated 100 tandem HD signal is then applied to a band-pass filter 42 to eliminate undesirable harmonics and extraneous noise, and a filtered 100 tandem HD signal is inserted into a mixer 44 into which has also been introduced a component of the 100 HD signal from the source. 30 distributed by the RF power divider 34. The filtered 42 can be any conventional band-pass filter. The mixer 44 may also be of conventional type similar to the mixer 40 heretofore described. The 100 MHz and 100 tandem HD signals combined in the mixer 44 to yield a signal of frequency equal to the difference in frequencies of the two component signals, i.e., tandem HD still modulated by the monitored brain wave activity. The tandem HD signal is amplified in an amplifier 46 and channeled to a demodulator 48. The amplifier and demodulator 48 can both be of conventional types. The type of demodulator selected will depend on the characteristics of the signals transmitted to and received from the brain, and the information desired to be obtained. The brain may modulate the amplitude, frequency, and slash or phase of the interference waveform. Certain of these parameters will be more sensitive to corresponding brain wave characteristics than others. Selection of amplitude, frequency or phase demodulation means is governed by the choice of brain wave characteristic to be monitored. If desired, several different types of demodulators can be provided and used alternately or at the same time. The demodulated signal, which is representative of the monitored brain wave activity, is passed through audio amplifiers 58B, C, which may be of conventional type where it is amplified and routed to displays 58A, B, C, and computer 60. The displays 58A, B, C present the raw brain wave signals from the amplifiers 58B, C. The computer 60 processes the amplified brain wave signals to derive information suitable for viewing, e.g., by suppressing, compressing, or expanding elements thereof, or combining them with other information-bearing signals and presents that information on a display 62. The displays can be conventional ones such as the types hereinabove mentioned employing electronic visual displays or mechanical plotters 58B. The computer can also be of conventional type, either analog or digital, or a hybrid. A profile of the entire brain wave emission pattern may be monitored, or select areas of the brain may be observed in a single measurement simply by altering the scan angle and direction of the antennas. There is no physical contact between the subject and the monitoring apparatus. The computer 60 also can determine a compensating waveform for transmission to the brain to alter the natural brain waves in a desired fashion. The closed-loop compensating system permits instantaneous and continuous modification of the brain wave response pattern. In performing the brain wave pattern modification function, the computer 60 can be furnished with an external standard signal from a source 70 representative of brain wave activity associated with a desired neurological response. The region of the brain responsible for the response is monitored, and the received signal, indicative of the brain wave activity therein, is compared with the standard signal. The computer 60 is programmed to determine the compensating signal, responsive to the difference between the standard signal and received signal. The compensating signal, when transmitted to the monitored region of the brain, modulates the natural brain wave activity therein toward a reproduction of the standard signal, thereby changing the neurological response of the subject. The computer 60 controls an auxiliary transmitter 64 which transmits the compensating signal to the brain of the subject via an antenna 66. The transmitter 64 is of the high-frequency type commonly used in radar applications. The antenna 66 can be similar to antennas 41, 43 and 45 and can be combined with them. Through these means, brain wave activity may be altered and deviations from a desired norm may be compensated. Brain waves may be monitored and control signals transmitted to the brain from a remote station. It is to be noted that the configuration described is one of many possibilities which may be formulated without departing from the spirit of my invention. The transmitter can be monostatic or bistatic. They also can be single, dual, or multiple frequency devices. The transmitted signal can be continuous wave, pulse, FM, or any combination of these as well as other transmission forms. Typical operating frequencies for the transmitter range from 1 MHz to 40 GHz but may be altered to suit the particular function being monitored and the characteristics of the specific subject. The individual components of the system for monitoring and controlling brain wave activity may be of conventional type commonly employed in radar systems. Various sub-assemblies of the brain wave monitoring and control apparatus may be added, substituted or combined. Thus, separate antennas for a single multi-mode antenna may be used for transmission and reception. Additional displays and computers may be added to present and analyze select components of the monitored brain waves. Modulation of the interference signal transmitted by the brain may be of amplitude, frequency, and / or phase. Appropriate demodulators may be used to decipher the subject's brain activity, and select components of his brain waves may be analyzed by computer to determine his mental state and monitor his thought processes. As will be appreciated by those familiar with the art, apparatus, and method of the subject invention has numerous uses. Persons in critical positions such as drivers and pilots can be continuously monitored with provision for activation of an emergency device in the event of human failure. Seizures, sleepiness, and dreaming can be detected. Bodily functions such as pulse rate, heartbeat regularity, and others also can be monitored, and occurrences of hallucinations can be detected. The system also permits medical diagnoses of patients, inaccessible to physicians, from remote stations.